Perfect.
Okie doke. Hello, I'm Holly. I've been a STEM ambassador now for almost 7 years. At the end, obviously, if you have any questions about the benefits of the STEM ambassador program, you can ask about that as well, besides what we're going to be talking about. I am an experimental materials scientist at the UK Atomic Energy Authority. And I would have said my research is a perfect example of interdisciplinary approaches to science, but now after seeing your slides, it might be multi. That's up for debate. Okay. At school, the way we approach science is by putting it in boxes, but that's not realistic. Any scientific research is multidisciplinary. You have to pull from different areas of expertise. Modern research and science, I would say it's like a spectrum, but I prefer to describe it as an interconnected web. I also think it's important to not put the scientists themselves in boxes. There are a lot of stereotypes about people in STEM, which for the most part aren't true. We're three-dimensional people from different backgrounds with all sorts of other hobbies and interests. A big part of our job is to break the mold in more ways than one. My current research is focused on the development of fusion-specific superconductor technology. What do I mean by fusion-specific? I want to use these superconducting materials in tokamak magnetic fusion reactors. Sorry. This type of research spans a number of different areas. I know people from applied superconductivity, different types of nuclear materials, and also spend a lot of time talking about the development of different techniques for materials characterization. To reach this point, I started out in pure chemistry before eventually going down materials chemistry and solid state chemistry route. Amongst my colleagues in this sector, there are a range of different specialisms. The most common I've seen are physics, nuclear fusion as a whole, and different types of engineering. I think it's highly important and beneficial to have people from multiple backgrounds looking into the same problem. Different backgrounds mean that everyone will have a slightly different perspective on how to approach the problem. To expand on my last point there, I've included a couple of examples I like to use to explain why it's important to have knowledge from different scientific disciplines. On the left, I've got the world's simplest electric motor, a wee video I took a couple of years ago. I think the obvious one would be you think electromagnetism, you think currents, magnetic fields, but you can also talk about this little demo in terms of the different materials there and their properties. You've got copper, a conducting material. You've got neodymium. It's a magnet, but it's also a metal. What do those things mean? You've got a battery too, and you can think about, of course, again, the electromagnetic principles, but the different components in the battery itself. And then you can also go into electrical engineering, electric motor, electric generator. They're very similar, just the other way around. It's here you're using generation of electricity to create the rotation, whereas with a generator, you're using rotation to generate the current. That's really fun. Microfaraday, all that kind of stuff. A lot of really fun engineering there. And as I alluded to just there, forces. This is a funny one. I do actually quite like to use this to talk about the forces you experience in a tokamak. The force acting on the wire, it's called Lorentz forces. And inside a fusion reactor, you'll have the plasma, the hydrogen plasma fuel, generating a magnetic field which interacts with the magnetic materials themselves, and that interaction between them can sometimes be strong enough to actually rip the magnets from what they're deposited on from the wall. Yeah, I think it's fun to show, okay, you've got this little demo, but on a big scale, it can be intense. On the right, I've put some stuff relating to photosynthesis. I think a lot of you are more biology teachers, so maybe this one's more familiar. With leaf, of course, you can think about it in terms of its structure, the different components, biological structure of the leaf, and then within that structure, you have chemical processes going on to actually generate the, what is it? It's carbon dioxide. Is it glucose? No, starch in leaves. You'll know. You'll know. But then you think, well, how did you get to the sugar or starch? It's you absorb light. That's an absorption spectrum, action spectrum, and then there you've got your link to physics as well. You've got all three different perspectives on the same process, the same, well, often beautiful plant. That's all from me for now. I hope that was helpful. A little blast of information for you. If you have any questions on, as I said, the STEM Ambassador Programme, anything I've talked about, if you want to know more about UKA, go for it. Thank you very much. I'll stop sharing my screen now.